And we're back. Today's lesson is 9.4, Testing for Independence. So, I've noticed that I have a little bit of a typo here. This is not pre the formulas. So, I'll make that change for next year. The formulas defining the intersection of dependent and independent events can help us test whether two events are dependent or not. All right, so independent events show that they are equal. All right, so we're going to talk about what this means, that these are equal, and dependent events says that they're equal if the probability of A times the probability of B given A. All right, so test one, if the product of P of A and P of B give you the probability of A and B, then A and B are independent. That's what the first one says. Test two, A and B are independent if the probability of B given A equals the probability of B. And we just talked about that with our red hair. And likewise, the probability of A given B equals the probability of A. So in other words, we talked about this with our red hair. So remember we said the probability of red hair given green eyes was not equal to the probability of red hair. One was way bigger than the other. So we knew those two were dependent. They were not independent. They were dependent. So the idea of having red hair was dependent on having green eyes. All right, and likewise, it's the same thing if you just switch them. And so the probability of A given B is the probability of A. If they were equal, so if, let's say, for example, if you could come up with, if, let's say, the probability it's going to rain given that it's a Monday. Well, I can tell you pretty much already, if I thought about what that means, that's the probability it's going to rain given that it's a Monday. Well, that would be still the probability it's going to rain. They would be equal to each other. There would be no impact on Mondays, although lately it seems like Mondays are raining an awful lot. But there actually is no dependence there whatsoever. So those two numbers would be equal, and then we would know they were independent of one another. Okay? Or not dependent. Sometimes they'll say things are not dependent, which means they're independent. But again, it's important to look at some examples so that we can kind of make sense of this on our own. So exercise one. Now again, on my typo, there was no spinner here, but it's the same spinner that occurs on the next page. So I just copied it here. You can pretty much easily make one. So it's basically an 8. Think about a pizza pie, right? So when you make this circle, you can make a circle the best way that you can. Then I just cut it in half again, and then cut it again, because that's how they cut a pizza pie. And you know sometimes when they're not cut well, like that last one, you get a smaller piece and a larger piece. All right, so draw that up first, if you need to. And it says the spinner below is spun once, and its outcome is noted. Let E be the event of getting an even. All right, so let E be the event of getting an even. Let P be the event of getting a prime, and let L be the event of getting a number less than 5. All right, so now let's go back and just talk about prime numbers. I think I probably did this earlier in this lesson, but prime numbers. The first prime number is the most special. 2 is the first prime number, and it's the most special because it is the only even number. And every other even number has 2 as a factor of it, so it will not be a prime number. And then every other prime number will just be a number that only has 1 and itself as its factors. So 3, not 4, 5, not 6, 7, not 8, not 9, because 9 is 3 times 3, not 10, and then 11, and so on. All right, so these are our prime numbers. So the probability, right here at A, the probability of getting an even number. So the probability of an even is going to be, how many even numbers are there? 1, 2, 3, 4 of them, over 8. And again, you can reduce it. You don't have to. 1/2. All right, B says the probability of getting an even given that the outcome was a prime number. So this is going to be the probability, of an even, given that it's a prime number, is going to be the probability of an even and a prime number over the probability of a prime number. And again, you can consider the denominators, and let's do the denominators and recognize that we can get rid of them right away. So the probability it's even and a prime number. Well, we only talked about there's only one of them, and that's 2. 1 divided by the probability of a prime number. So the prime numbers are 2, 3, 5, and 7. So there's 4 of them. All right, so again, I'm sorry, I did exactly what I didn't want to do. 1 out of 8 over 4 out of 8. The 8s can cancel, and you get 1 over 4. All right, so these are the actual probabilities. But when you have the same denominator, you can just count the numerators and the top and the bottom there. So it just turns out to be 1 over 4. All right? So C says the probability of getting an even integer given that the outcome was a number less than 5. All right, so what is this going to look like? So this is going to be the probability of an even integer given a number less than 5 is equal to the probability of an even and a number less than 5 divided by the probability of a number less than 5. All right, so even and less than 5. 2, 4, and that's it. So 2 of them. And the probability of less than 5, so that's 4. So it's 1/2. So D says, which event does E depend on? P or L? How can you tell what is a reasonable test? All right, so the first one is the probability of, actually I want to keep that last one up there too, because we have the probability right here. Here are the important numbers we have. Here is the probability of E. Here is the probability of E given P, and here is the probability of E given L. So as you can see, the probability of E is equal to the probability of E given L. So that tells me that those two are independent of one another. All right, but you can see how the probability of E given P is not equal to, so these two are not equal to each other, so there's dependence going on there. So what do we have to say here? We can say E depends on P, all right, because the probability E, the probability changes, all right? So why don't we write that differently? Okay, forget about that. Sorry about that. How about we say E is dependent. How about we say it that way? E is dependent on P because the probabilities in A and B are different. Or let's say are not equal. I think that's a better way to say it. All right. Now, E is independent of L because the probabilities in A and C are equal. All right, I hope that's making sense to you. This goes right back to our probability with red hair and green eyes, or the probability of rain given that it's a Monday. All right, so if they're equal, then they're independent of each other. If they're not equal, it means that something happened that skewed that number off a little bit. All right. Sometimes you can use a little bit of common sense, but we want to use math to drive what we're doing right here, okay? But using common sense is always a good way to, you know, just check yourself. All right, when you're finished writing, meet me at exercise 2. A survey of 57 sixth graders was done to determine which subject was their favorite. The results are shown in the table below, sorted by gender. So this is what they call a two-way table again. All right? So, does it appear, based on the data of this table, that the preferences for math as a favorite subject has dependence on a student's gender? Well, that's a silly question because everybody loves math the most, whether it's male or female. But then it says show the analysis and explain your findings. So this is what a statistician might do to say maybe more boys like math, maybe more girls like math, or is math just, is it just dependent on what your gender is? So what we're going to do is, first thing we're going to determine is what is the probability of math? So the probability of a person liking math should be 100%, but it's not. Let's see. So the probability of a person liking math is 18 out of our grand total of 57. And I calculated that to be 0.32. Now, you could leave it as 18 over 57, but the numbers and the denominators are going to be changing, so you can see how you'll be able to see why I change it to a decimal. So the next one is going to be, what's the probability of math given that the person's a male? Well, remember what that means. This is going to be the probability of math and male over the probability of male. So this is equal to the probability of math and male. Math and male, 10. Out of the probability of a male, all males, 27. So this is equal to 0.33. I'm sorry, did I do my math wrong? It's 0.37. And the last one I'm going to do is the probability of a math given that it's a female. So that's the probability of math and female over the probability of female. So that's going to equal to probability of math and female. So that's going to be 8 over the probability of all females, 30. This is female, 27. So, since none of these are the same, because this is the one we're comparing it to. This is the one we're comparing it to. So if either one of these was relatively close to that, there might be a margin of error, which is something that we're going to talk about a little later on. All right. If these were relatively close to that, then there would be independence, or there would be no dependency. But because there definitely is, you can see how females kind of really don't like math, and males are higher. So that's actually a pretty good thing. So if we have to show and explain your findings, so because, I hate using the word because, starting with sentence with because, but I guess we can. Because the probabilities are not equal, we can assume gender plays a role in choosing math. as a favorite subject. Another way that you could write this is that based on the data, based on the calculations, because the probability of math given male and the probability of math given female are not equal to the probability of math, then math is dependent on gender. You know, you can use a little bit of the wording. If you never know what to do, I always will tell you, go back to the wording, all right? So you might want to say, the preference for math as a favorite subject has dependence on a student's gender because, all right? So you can use some of the wording from the question in order to answer it. If by chance you're really not able to think of the wording that's necessary. All right, going down to B. Does it appear, based on the data in this table, that the preference for social studies as a favorite subject is dependent on a student's gender? So we're going to do exactly the same thing here. The first thing we're going to do is, what is the probability of just social studies? So that's going to be the probability of social studies and, I'm sorry, it has, social studies is just going across. Let's erase this. So probability of just social studies is 19 over 57. So now, what's the probability of social studies given a male? So that's going to be the probability of social studies and male, which is 9, over the probability of male, all male, which is 27. And the probability of social studies given a female, remember the numerator is going to be the probability of both social studies and female, which is 10, over just female, which is 30. So this is equal to 0.33. This is equal to 0.33. And this is equal to 0.33. So what do these calculations tell you about the impact of gender on liking social studies? Well, this appears, so what might you say here? If we want to use our wording, so the preference for social studies as a favorite subject is not dependent or you could say independent of gender. Pretty cool, right? So there's a really nice test for dependence that can be applied easily and comes from our formula for conditional probability from the last lesson. So, given that the probability of A given B is the probability of A and B over the probability of B, all right? So if you just look at the bottom A, if A and B are independent, then write this formula and solve for the probability of A and B. So if they're independent, I know that the probability of A is equal to the probability of A given B. So I know the probability of A is given by the probability of A and B over the probability of B. And then if we cross multiply, I know that the probability of A and B is equal to the probability of A times the probability of B. Isn't that cool? So this is that second test for independence that we talked about at the beginning. So the probability that a person is left-handed is 12%. Oh, this is nice. They're actually giving us stuff here. So the probability a person left-handed is 12%. All right, the probability they have brown eyes is 42%. The probability that they have brown eyes and are left-handed is 2%. So what are they telling us? The probability that they're left-handed is, remember, we're talking numbers now. We're in math, people. We talk numbers, we don't talk percents. The probability of brown eyes is 0.42. Sorry. And the probability of left-handed and brown eyes is 0.02. All right, now if we did this the old way, okay, is there an event having brown eyes dependent? So if we did it the old way, we'll do it two different ways. Let's see if I can just somehow bring this up a little bit. And I know you don't have a lot of room here, so I'm sorry. Move over to the side a little bit. So what we're saying is the old way says that what are they asking us for? Totally losing it here. Is the event of having brown dependent on left-handed? So the probability of brown eyes given left-handed is equal to the probability of both over the probability of left-handed. So this is 0.166. All right? So we can basically say that the probability of brown eyes, so since 0.42 does not equal 0.166, we know that they're dependent. They're not equal. The new way is going to be to see if 0.02 is equal to 0.12 times 0.42. And if you get this, you get 0.02 is equal to 0.0504. So because they're not, they're also dependent. All right? So, two different ways there. Doesn't matter which way you use. Sometimes they give you the information to do, like this time they actually gave this to us. Enough information. Sometimes they don't give us enough information, so you can't use one. You have to use the other. And hopefully you'll see some of those examples when you get into 9.5 independent practice. All right? I'm going to remind you that 9.5 are Regents questions, and those are the ones you should really be making sure you're persevering solving them and see if you can come up with the correct answers. Everything I do, I will upload the solutions to make things easier for you. But like I always tell you, always make good choices, and I'll see you next time.